YAML, sklearn, linear model, netpath. Description. The netpath function in scikit-learn's linear model module implements the elastic net regularization path. It calculates a sequence of models, each with a different value of the regularization parameter L1 ratio, while keeping the other parameters constant. This allows exploring the trade-off between model complexity measured by the number of non-zero coefficients and prediction accuracy. Inputs: X a 2D array of shape n samples, n features representing the training data features, Y a 1D array of shape n samples, representing the target values, L1 ratio of float between 0 and 1 representing the mixing parameter. A value of 0 corresponds to ridge regression L2 penalty and a value of 1 corresponds to lasso regression L1 penalty. Apes a float representing the tolerance for the stopping criterion defaults to 1e-3. N alphas an integer representing the number of alphas to compute defaults to 100. Alphas an array of floats representing the values of the regularization parameter alpha to compute. Fit intercept a boolean indicating whether to fit an intercept term defaults to true. Normalize a boolean indicating whether to normalize the data defaults to false. Precompute a string or array like indicating whether to precompute the gram matrix defaults to false. Copix a boolean indicating whether to copy the input data defaults to true. Verbose an integer representing the verbosity level defaults to 0. Outputs: alphas a 1D array of shape n alphas, representing the values of the regularization parameter alpha for which the models were computed. Coefficients a 2D array of shape n alphas, n features representing the coefficients of the models for each alpha. Knitters a 1D array of shape n alphas, representing the number of iterations required to compute each model. Steps: the netpath function calculates a sequence of elastic net models, each with a different value of the regularization parameter L1 ratio. For each value of L1 ratio, the function uses a coordinate descent algorithm to solve the optimization problem for different values of alpha. The resulting models are stored in the coefficients output, along with the corresponding alpha values. Metrics: R-squared, a measure of the proportion of variance in the target variable that is explained by a model. Mean absolute error may, a measure of the average absolute difference between the predicted and actual values. Mean squared error MSE, a measure of the average squared difference between the predicted and actual values. Visualization plots: coefficient path plot, a plot of the coefficients for each feature across different values of alpha. This allows visualizing the sparsity pattern of the models and the impact of regularization on feature selection. Regularization path plot, a plot of the regularization parameter alpha against the corresponding R-squared, MA, or MSE values. This allows visualizing the trade-off between model complexity and prediction accuracy. Fine-tune parameters: L1 ratio controls the balance between the L1 and L2 penalties. A higher L1 ratio emphasizes sparsity, while a lower value emphasizes the ridge penalty. Alpha, the regularization parameter, controls the strength of the penalty. A higher alpha value leads to more regularization and sparser models. Apes, the tolerance for the stopping criterion. A lower value results in more accurate solutions but can be computationally expensive. Uncertainty methods: confidence intervals for the coefficients can be calculated using methods like bootstrapping or cross-validation. Bayesian inference: a Bayesian approach can be employed to incorporate prior information about the coefficients and estimate their posterior distributions. which can be used to quantify uncertainty. Challenges and fixes. Challenge 1: overfitting. When the model is too complex, it may overfit the training data, leading to poor performance on unseen data. Sample use case that resulted in Challenge 1: a high-dimensional dataset with a large number of features and a small number of samples. Fixes to Challenge 1. Increase the value of alpha to introduce more regularization. Use cross-validation to evaluate model performance and select the optimal value of alpha. Consider using feature selection techniques to reduce the number of features. Challenge 2: computational complexity. Computing the regularization path can be computationally expensive for large datasets or a large number of alphas. Sample use case that resulted in Challenge 2: a very large dataset with millions of samples and features. Fixes to Challenge 2. Reduce the number of alphas to compute. Use a more efficient algorithm like stochastic coordinate descent. Consider using parallel computing to speed up computation.